The next set of processor that we have to go through is 80486. So before going on to the next processors, we'll understand every processor by its differences. So far we have discussed 8086, 286, 386, 486, and then goes to your Pentium, which is again 586. The best way that you can understand every processor is whenever you are preparing for the examination, you prepare all the processors by its features. So what comes under features? The common things that come under features will be the ALU, the data bus, the address bus, the total memory, and in addition modes. In 8086 we have minimum maximum mode, in 286 we have 2 modes, 386 we have 3 modes, 486 has a cache, Pentium will have a cache, one has a, so each and everything have the differences, and whenever you relate every processor, these are the common set of features that you have to mention everything. And apart from the common set of features, there will be the additional features that comes with each and every processor. So there is nothing much detail that we can discuss about 486. In 486 we have a cache and we have a floating point unit inbuilt. So floating point operations are inbuilt for this processor. 386 similarly have a barrel shifter and has 3 modes. Here the special feature is the paging, and here is the protection is a special feature, and we have a processor extension interface. So does 8086. We have a maximum mode, and the last major processor that comes in is a Pentium. So Pentium is again a 32-bit processor. One difference that we come across from the rest of the processors is the data bus and the ALU are in line with everything. So it's a 16-bit processor and a 16-bit data bus. It's a 16 and 16, 32-bit processor and 32-bit data bus. Here the processor is a 32-bit processor, but the data bus is 64-bit. So that is one change that we have in this processor. And we have a separate, we have cache which is separate. So we have a code cache and a data cache separately. So each of 8 KB each. So total 14 address lines are required to select the code cache and data cache. So why do we have this code and data cache separately? Because the code part will go into the code cache, which is going into the decoder, and then the control unit will select the appropriate option in the ALU. Similarly, whenever we go into the execution part, it requires the data to be executed. So the data operands can be found in the data cache. So this partitioning will help the processor to execute much more faster. So that is what is a new feature in the Pentium, and so does the architectural diagram of Pentium, which is pretty much important, and it follows something called as superscalar architecture. Ideally we have a pipeline. So pipeline is about fetch, decode and execute. So we call it cycle 1, cycle 2, cycle 3 and so on. So instruction 1 ideally falls under fetch, decode, execute. And while I1 is decoding, if I send I2 in the fetch stage, and while I1 is executing, you can fetch I3 and decode I2. This looks like the processor is executing the things in parallel, but it's not executing the things in parallel because we have only one execution unit. But it seems like it is execution parallel, which is the similar thing that we call as a pipeline. So this evolves into a superscalar architecture followed by Pentium. So how does it work? Instead of having one execution unit, your Pentium processor will mimic 2 different execution units, and it doesn't have a 3-stage pipeline, it has a 5-stage pipeline. So what it does in this 5 stages? So ideally it will fetch Data is stored in the data cache, code is stored in the code cache, and then it decodes the instruction, and then it will put it in the two different pipelines. And here the pipeline breaks into two. There is another decode for finding the instruction, and then the execution, and then storing back the results. And the similar pipeline you have, which is ditto of what happens in this. So usually we call it a U pipeline and a V pipeline. 80586 or Pentium has a 5-stage pipeline, and the pipeline diverges after the decoding of the instruction. How it happens is, you can do two different operations simultaneously. It seems that we can do two different operations simultaneously. How many ALUs are there? There is only one ALU, but it mimics like two different execution units. So it operates so fast such that the data gets executed and doesn't wait for the next data to be getting in. That is how the parallelism is evolved, and such an architecture is called as a superscalar architecture. This is the first ever processor which does that. And U stage pipeline and a V stage pipeline. Along with this, we have a separate floating point unit in your Pentium processor. Along with the floating point registers are of size 80 bits. So we have a 64-bit mantissa and a 16-bit exponent to store the floating point operation. So if I just ask how many execution units are there for Pentium, maybe you can say 3. 2 integer execution units and a floating point execution unit. That is how the superscalar architecture is evolved, and that is how you speed up the operation of your Pentium processor. Another new feature that we had is we have a separate code cache and a data cache. So now you might have understood why we are using this 64-bit data bus. Whenever you are accessing the floating point operations, we may end up using the 64 bits of the data bus, getting in the data or storing back the data. And then another processor evolved to something called MMX. I think many of you are getting confused with MMX and MMU. MMU is a memory management unit, whereas MMX is a multimedia processor. Every day when we are computing something, soon after the introduction of GUIs like Windows or Linux operating systems, we need to render a lot of graphical intense operations, maybe starting with photos or videos, sound. All these things require a set of vector processing which is done by the floating point unit, and there is a separate unit called MMX which does that. So MMX carries all the features of Pentium, and it separately have 57 MMX instructions. That means there is a separate hardware block dedicated in this. It is specifically doing the multimedia operations. These soon evolved into something that you call graphic processor that we are using today. So what do we do with the graphic processor? We use it for rendering the videos, or rendering the image manipulation using Photoshop or something, or play games. What do they specifically do apart from this integer is they do the floating point operations. They do the intense floating point operations to pick up the, and that is where we have multiple data types related to the MMX. After MMX, we had this Pentium Pro, and then we have dual core processor, and then we have a Core 2 Duo. So Core 2 Duo is Intel's 64-bit processor, and I think Pentium 2, a new feature that Pentium 2 adds is a level 2 cache. So this is what we call a level 1 cache. All the data that we are getting in is segregated into code and data. So instead of segregating soon after we are storing it in a level 2 cache and then segregating into code and data cache. So this is what we call L1, and this is what we call L2. So today's computers, we have level 3, level 4 cache which stores. So ideally, if you look at it, L1 should be lesser, L2 will be more, because we need to put lot of the data or the code in the queue before we send it to the much levels of partitions. So with this, I think we can close the Pentium and all the set of architectures we have. Today's processors like i3, i5 and i7, they seem to be multi-core processors. Multi-core in the sense Core 2 Duo is a multi-core. Multi-core is we have two physical cores or maybe dual core. Is a two different cores. Our mobile phones come up with quad core or octa core. What happens in this is we have 4 or 8 physical cores. That means if I have an AX register here, you have an AX, you have an AX and you have an AX. You have an ALU here, you have the same ALU in all the cases. That means we have multiple schedulers. The operating system should be so capable, they have to schedule the jobs into multiple processors and get the things done. And in the multiprocessor environment, like we did with this Pentium, here how many ALUs we have? We have only single ALU. But it seems like it is executing 2 different operations. That evolved into something called as hyperthreading. So hyperthread is a simulated hardware where the single core or a single processor try to behave like 2 different processors. That is evidently seen in all the today's processors. So we say i3, i5 and i7. So i3 is a dual core processor. But if you look at the task manager, you can see 4 cores in it. So ideally there are 4 logical cores. That means 2 physical cores and 2 hyperthreads. So if I have 2 physical cores and I have hyperthread 1, hyperthread 2, a logical processor 1, logical 2, logical 3 and logical 4. Physically there are only 2 processors. So how is this working like this? It is using a processor and a hyperthread to form a single core. That is how the hyperthreading works, and this is similar to what we have seen here. So multi-core and hyperthreading and the superscalar architecture in combination had increased the speed of the computation like you have never imagined. These are the things that are pretty much common in the set of processes we have seen. And then the categories and categorization of the process. The processors are categorized into multiple based on architectures. That means Intel is not the only company that produces the processor. There are many companies like Motorola, MIPS, PowerPC, ARM, Samsung. What all these people do is they create their own processors. But every processor being independent doesn't help the operating system developers to build an operating system. So how do you ideally build that? There are architectural rules that everyone should follow in order to evolve the process. 2 such things are CISC and RISC. So I'll quickly make you understand with the differences. So RISC is a reduced instruction set computer, whereas CISC is a complex. It looks like the names doesn't give a lot information about it. CISC is what we have seen in the Pentium processor so far. It will have more number of instructions. So instructions will be more, whereas RISC will have less number of instructions. I'll let you know with a simple example how these things vary. Your memory has a code and you have registers and then ALU. Ideally, when we are bringing the data from the memory, we need to go to the memory, we need to store in the registers, and we can do it in the ALU. Or we can call the data from the memory and store it in the ALU. An example would be add AL comma SI. It adds the data from memory to a register and stores in a register. And the example for this would be add AL comma BL. Here the data is operated only within the registers. If you look at what takes more time, this will take more time than this, because you have to go to the memory, fetch the data, bypassing the registers and do the operation on the ALU. Now, who will have more number of addressing modes? who will have more number of combinations for the addressing mode is, this will have more number of combinations, because ALU can interact with memory. If I say there is only one way, this is path 1, and the other way is you can have all the 3 ways, there the combinations will be more. So CISC falls under this category. So you can access with ALU, can access a memory or a register. That means we'll have more number of addressing modes. RISC architecture on the other way doesn't allow you to do this. So whenever you want to add something or subtract or compare the values, the only way you can do is you interact with the registers. So how will the registers get the data? The registers will use the data transfer instructions such as load and store. Those are the only 2 instructions which will talk with memory and get the data. So what will ALU do? ALU will always go to registers, fetch the data and store back the results. So load will bring the data and the operations are done between ALU and registers, and store will store back the data. So only 2 instructions will interact with the memory, and rest of the arithmetic, logical or whatsoever instructions we have will operate only on the registers. That's how we will differentiate RISC and CISC. That is why we will have less number of addressing modes. Who will have more number of registers? Who require more number of registers? Obviously RISC, because every data is getting stored in the register. So we need to have more and we need to have less. Who will have more number of instructions possibilities? Again, CISC will have more number of possibilities compared to RISC. Where are these being used? These will be used in general purpose operations, which require more number of combinations, and this will be more evidently seen in the application oriented. Maybe your mobile phones come with ARM processor. Your mobile phones uses RISC architecture, whereas your laptops uses CISC architecture. So this will be the couple of differences which will help us understand what is RISC and CISC. And again, the number of cycles. RISC will take multi-cycles to complete the operation, whereas CISC will ideally take 1 or 2 or a static number of cycles. Why this? How this will help? This will pretty much help in synchronizing the jobs. If everyone completes in one step, all the 10 instructions will complete in 10. But if you look at the multi-cycle, move will take 1, add will take 2, or compare will take 3. I can't figure out how much time my program is to take to finish the amount of code. So that is pretty much difficult for the scheduler to schedule the jobs, whereas it is pretty much simple for this. So who will have more number of lines of code? Instead of doing a copy here, I have to copy to register and store it to ALU. So definitely RISC is more software driven. So you need to write bulk of code, whereas CISC you can render the program using less number of instructions. So these will be the typical differences between a CISC and a RISC machine. Another set of this is how the processor is defined, and related to memory there are 2 different modes. One is a Harvard architecture and a von Neumann architecture. So to put it in a simple way, if you have a RAM plus ROM on a single chip, you call it a von Neumann. If you have a separate RAM and a separate ROM, you call it a Harvard architecture. That means you have 0 to F addresses. Here you can have more number of addresses or more number of memory accessibility can be done. So von Neumann architecture and the Harvard architecture. So CISC and RISC. These are the standards that will help any processor to be generated or to be developed based on the set of rules that were given. So this will end the whole processor part of the syllabus. And the last topic that we had here will be the microcontrollers. Processors, so far we have seen, we are using the processors in our computers for the general purpose operations. The examples where we use them will be your laptops and your mobile phones, whereas microcontrollers are more application oriented. Suppose there is an example of a fire sensor system in your classrooms. The simplest job that it does is it senses whether the fire is there or not and execute a task, maybe ring an alarm or turn on a water sprinkler. How much amount of code it actually requires is a simple if-else algorithm. So is it really code intensive? No. Do you require GBs and GBs of RAM like we have seen in 80, 286 or 386? No. A simple memory and a simple processor should have been sufficed to run that application. How many such applications we see around every day? We see washing machines, microwave ovens, smart watches and whatnot, your lift and everything. Every device that you see will be based on a simple operation and a single application oriented systems. What do they, do we need a i3 processor to run that? Definitely no, that would be a waste of resource. There is an evolution of something called as a microcontroller, which are having less resources and can do a specific operation. So if you look at the architecture of a microcontroller, you have a CPU inside it. That means you have a processor inside it. Along with the processor, you have a RAM, you have a ROM, and maybe you will have a clock. You will have timers. Why do you require a timer? Every operation that you see is time based. Lift. After 5 seconds, the door should close. Or after every 1 second, should I check whether the fire is there or not? Or after 5 minutes, should I run the spinner or the dryer in the washing machine? So every operation are usually time based. So we require a timer which does the timing part and maybe interrupts and more on. So all these things come on a single chip. In a processor, how it differs is we have a CPU here, we have a RAM, we have a ROM, we have interrupt controller, we have something else, and they are different blocks interconnected together. Why? Because we require modularity. Maybe a laptop, I end up filling up with all the movies, I have to extend my hard disk. Or a mobile phone, I might want to extend my SD card to save a lot of photos. But this never happens with a alarm system in your classroom. So it doesn't need a 1 GB of storage, or it doesn't need to play songs for us. So we don't get any new requirements every time we use that. So washing machine is washing machine and there is nothing more to it. A fire sensor is a fire sensor and nothing more to it. But a laptop, maybe I want more RAM, maybe I want to play games, or maybe I want an external hard disk, or I want a graphic card. So all should be modular. So processors are more modular based systems, whereas controllers are tightly packed and how are they well resourced? Definitely no. So we don't require a bigger we require less resources to run a microcontroller, and they would definitely be cheaper, and speed is never an issue for us. So instead of a speed, what do we need to really care for is the amount of job. So is the job done or not, and they are really not time critical. So microcontrollers are how they differ from a microprocessor. So the single difference that you see is they are in a single chip, they are more application oriented, they are less resourced, and they are more cheaper. And again we have classifications. We have 8-bit, 16-bit, 32-bit microcontrollers. We have RISC based and CISC based microcontrollers. We have Harvard and von Neumann based microcontrollers. So everywhere the microcontrollers differ with respect to their own purposes. So this will wind up the whole syllabus that we have in our microprocessors. Lastly, there are a couple of suggestions that I want to give you when you are trying to prepare or write the exams. So whenever you are preparing for the processors, we have 3 to 4 different architectures. 8086, 286 and 386 have and Pentium have the architecture diagrams. So study them in comparison. So everything have bunch of things in common. So features. For all the processors we have features. Study them in common. We have architectures. We have architectures in 86, 286, 386 and Pentium. Study all of them in comparison. So if you study all of them in comparison, it is the better way to remember. We have flags, we have registers. For all the above, we have all the flags and the registers. And then the important thing with the instructions and addressing modes, you have to mention the name, the syntax, the example, and the operations. So this is one important instruction or the format that you can follow. Or whenever you are talking about some bits, so we have a descriptor, page descriptors or segment descriptors. We have frames. So draw the frames pretty neat, maybe not the way I have drawn here. So we have P and A. So just mention what is P and mention what is 1, the definition of what is 1 and what is 0. Or you want to explain about a carry flag, so put C. So C is a carry flag. So when does it execute and what is 1 and what is 0, maybe an example. So this is the order that you have to follow when you are maybe attempting the exam, which will help the evaluator evaluate your paper in a much better way. This is the same for addressing modes and instructions, and then the timing diagrams. So the timing diagrams are pretty much simpler. We have already discussed earlier. Only one set of timing diagram is enough, and everything follows a similar pattern. So except for all these, in the CO3 and CO4, all we have are the features, and there are only couple of diagrams which are the architectures and the descriptor privilege levels, and that's it. So I hope you can wind up studying the examinations in the way that I have just said, which will help you prepare better for your exams. So hope you will do well in the exams. All the best.